Well, that's just amazing. I don't know about you, but these are very important take-home lessons. For example, Nathan, one of my take-home lessons would be that it would be environmentally sound for the Hebrew University to purchase electric cars for its faculty members. I think that would be a good idea, no? Okay. So again, thanks Rasha and Nathan for those amazing discoveries and insights. We've all been increasingly hearing about big data. This is the digital revolution and the ability to aggregate, integrate, and analyze an unimaginable quantity of data, which has unleashed a wealth of life-improving capabilities, and we're only at the beginning of this revolution. Though she's currently at a conference at Oxford, we didn't want you to miss meeting Professor Michal Rosen Zvi, Director of AI for Accelerated Healthcare and Life Sciences Discovery at IBM Research, and a new member of the Faculty of Medicine who will be involved in its Center for Computational Medicine. Michal is a computational physicist who will share with us virtually how AI is already being used to accelerate drug discovery. After that, you'll meet Mo Wengner and Zvi Michelson, who are working to ensure that the next generation of all backgrounds can be part of the digital revolution. Mo, a computer science and cognitive science recent graduate, and Zvi, a graduate student in computer science, founded ForStart, a program that teaches youth from underrepresented communities the basics of coding together with a healthy dose of self-confidence. Continuing the theme of impacting the next generation, we'll then hear from Ariela Lehman, an alumna of the Revivim Teacher Training Program who has leveraged her love of teaching and her master's in Jewish history to help her high school students appreciate the beauty of Jewish culture. Please.
Good evening. I've got some great news to share with you. We're expecting many wonderful scientific discoveries these days emerging at an unforeseen pace thanks to AI technologies. Come join me behind the scenes of how scientific discoveries are made to get a sense of how we got here and where we are headed along this exciting journey. In ancient times, a scientific discovery was made through experimentation. If you take opium poppy, for instance, people probably stumbled upon it by coincidence in different parts of the world long ago. This pain relief drug is among the world's oldest known drugs. In fact, remains related to opium usage by humans were found in an Egyptian tomb from the 15th century BC. The seminal work of Sir Francis Bacon, Novum Organum, published 400 years ago, introduced the scientific method to the world and marked the change of an era. His work introduced rigor to scientific discovery with a process that starts with a question, followed by a study that leads to a hypothesis that is tested in an experiment that is the foundation of a new theory. This is the era where models of the atoms were studied, the periodic table was discovered, scientists discovered molecules that are combinations of different atoms. Going back to the poppy example, this is the time when the extraordinary pharmacist Friedrich Sertuner successfully isolated morphine from opium poppy in its pure form. In his scientific quest for finding the optimal dose, he performed experiments on various human beings, first and foremost on himself, which made him an addict who advocated for safe use of this powerful drug. Computational methods played a significant role in the next phase of scientific discoveries. Once methods were developed to extract structure of molecules from X-ray images, to compute masses from mass spectrometer, scientists who suspected that morphine-like molecules naturally exist in our brain found endorphins and were able to sequence their chains of amino acids. Credit for these findings goes to a whole group of cooperating researchers. I will not list them all, just mention the two professors from University of Aberdeen who were the first to isolate the molecule from a soup made of pig's brain 50 years ago. What happens when computers are abandoned and machine learning technology evolves? We are expected to a whole new level of understanding that can only be created from the multiple sources of masses of data accumulated over time. Initial breakthroughs were in analyzing text. Large digital cohorts of textual write-ups were among the first publicly available datasets. Over a decade ago, as a young postdoc at UC Berkeley and later at the Hebrew University's Computer Science Department, we introduced machine learning models to analyze large text corpora called the author-topic models and showed their usefulness in different tasks, such as predicting content that authors will generate and automatically proposing links to websites with relevant content. As large genomic datasets were made available, the same models were adapted for discovering new patterns of gene expressions or mutations associated with various illnesses. Such studies are typically performed per domain and data model. And today, as we speak, we are experiencing a grand convergence of knowledge in biology, chemistry, and medicine, with data-driven models applied to different modalities that lead to a whole new level of discovery. The world of drugs requires an understanding of the chemical properties and their impact on the human body, from the molecular level and the physics of interactions, to learning from digital pathology of tissue, medical images of organs, and blood tests, and other measures from the whole body. Current technologies enable this convergence. The cloud environment enables new scale of computing. AI technologies such as deep learning and transformers are showing promising results in many different fronts, from finding protein structure from its sequence, to generating new molecules given a protein target, to inferring biomarkers from high-dimensional retrospective data. Let me leave you with two concrete examples of the current exciting converging phase that are just the tip of the iceberg. Example number one. A team from the Hebrew University's Department of Chemistry and Faculty of Medicine published a paper in PNAS last year about a generic methodology that extracts structural data from living intact cells for any protein of interest. They showed how their method reveals the full structure of certain proteins of severe acute respiratory syndrome coronavirus 2, SARS-CoV-2, previously unknown due to the instability of these proteins outside of the cellular context. Example number two. I have worked with my IBM research team on developing AI technologies to automatically detect breast cancer in medical images from screening exams. In fact, in two recent publications in radiology, one with Asuta from Israel and the other with Johns Hopkins University, we have shown that the technology is on par with radiologists' performance. In a recent study with my PhD student from the Faculty of Medicine and other colleagues, we were able to show that when combining images with clinical history, the technology can already relatively accurately identify the pathology type of a lump based on the screening exam data. This finding holds the promise of identifying prognosis biomarkers in clinical data and/or the images. The possibilities are endless. To rephrase Talmudic saying, if all the seeds were ink and all the reeds writing pens and the heaven and earth scrolls and the people of the world were scribes, there would not be enough room to write all the scientific new facts regarding health, disease, and their remedies that we are about to discover.